Okay, this is a fall 2023 Organic Chemistry 1 Exam 4 on radical and ionic reactions review. So as we proceed through this review, you'll notice in the left column here under the question number, the correct answer is shown in green. So those are the correct answers, and then what I'll try to do in this recording is give you my thoughts on how you go about solving each of these questions. So question number 1 is asking you which one is 2,3,4-trimethylpentane. So looking at the nomenclature for that compound here, and what I'll do is just draw some notes in red. So the parent is a 5-carbon alkane. So the longest chain has to be 5 carbons. And then we see we have methyl groups at the 2, 3, and the 4 positions. So with the green highlighter, as you go through A, B, C, and D and identify the longest chain, and I'll just start from the left. We have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So they're all pentane derivatives. So we can't eliminate anything based on the count. So really what we have to do is see where the substituents are on that chain. So as we number 1, 2, 3, 4, 5, we can see that at the 2, the 3, and the 4 positions are methyl groups. So that's going to be the correct answer. B has methyl groups at the 2 and the 3. C is 2 and 3. D is 2, 3, and 4. However, that has 4 methyl groups. So you can use that logic in eliminating wrong answers there. Question number 2. A compound with a uniqueness set of 6 unique H's, and then that ratio 6 to 3 to 3 to 2 to 2 to 2. And your best bet here is to just draw all of these out. So let's go ahead and do that in the black pen here. So one thing to notice, they're all hexane derivatives. This is going to get a little jammed up here based on space, but let's go ahead and draw that out. 1, 2, 3, 4, 5, 6. And then at the 3 and the 4 positions are methyl groups. And what you'll do is just figure out the uniqueness set there. This actually has a symmetry to it. So we'll change the pen color. And we can say that as we're going along, those are equivalent. So that's 1 set. These are equivalent. That's 2. These are equivalent. That's 3. And then these methyl groups are equivalent. So that has 4. So we can eliminate that. So 2, 5. So 1, 2, 3, 4, 5, 6. So 2 and 5. And when we switch off the color here, there's symmetry as well. So those methyl groups are all the same. That's 1 set. The methine, 2. Then the methylenes, 3. So that has 3, and we can eliminate B. So now 3-ethylhexane, 1, 2, 3, 4, 5, 6, 1, 2, 3, and ethyl. So we're going to have symmetry here as well. So these methyls are the same, 1, 2, so that's the same. These methylenes, that's 2 sets, 3, 4, 5, and 6. So this actually has 6. So now let's go in and figure out the ratio of the 6. So we said the methyl groups at the end were the same. So that's 6. Then we have the methylenes, those are the same, so that's 4. Then we have a 1 going down the chain, then a 2 and a 3. So we can see that even though it's 6 unique sets, it doesn't meet the 6 to 3 to 3 to 2 to 2 to 2 that we're looking for. So the answer is D, but let's go ahead and analyze that anyway. And again, apologies for the space here. 1, 2, 3. So dimethyl 4, 5. 1, 2, 3, 4, 5, 6. So as we proceed along this chain, we have 1 unique set, 2. We have a quaternary carbon, so that doesn't have any. The methyls are the same. So 1, 2, 3, 4, 5, 6. So if we're starting from the highest, the 2 methyl groups here, that gives you 6. The terminal methyl groups give you 3 and 3, and then you have these internal methylenes. So here, here, and here, and then that gives you your 2 to 2 to 2. So your 6 unique sets there that meet that requirement. So question 3, again, the correct answer is B, but let's go through the logic here. A branched C8H18 derivative that generates the most monochlorinated derivatives when treated with chlorine. So again, this is when you have to draw out the structures, then determine the unique sets, and then from that, you're going to basically extrapolate that the one with the most unique sets of H is going to give you the most unique monochlorinated derivatives. So we have a butane derivative. So 1, 2, 3, 4. Then at the 2 and the 2, we have methyls. 3 and the 3, we have methyls. So overall, this only has 1 unique set of H. Okay, so now we have a heptane. So derivative. So 1, 2, 3, 4, 5, 6, 7. The 3 position is a methyl. So there's not any symmetry here. So we have 1, 2, 3, 4, 5, 6, 7, 8 unique sets. So far B is the winner. Let's go on to C, which is 3-ethyl, 3-methylpentane. So 1, 2, 3, 4, 5. And then we have ethyl at the 3, and then methyl as well. So this does have symmetry to it, so quite a bit of symmetry. So this, and this are the same, so that's 1. The methylenes, 1, 2, 3 are the same, and then that's different. So overall, it's 1, 2, 3 unique sets. So B, again, is still the winner. And then finally, D, hexane, that's a 6-carbon chain. So we'll draw that 1, 2, 3, 4, 5, 6, 2, 5. And we actually sort of did this already in question 2. We had 2,5-dimethylhexane, but let's go through it again. So the methyl groups, 1, 2, 3, 4 are all the same. So that's 1 set. Methine, that's another, and then methylene, so that's 3. So this one we get 3. So overall, 8 is the most. And so question 4 says C8H18 derivative that will generate 2 equivalent tertiary radicals upon homolytic cleavage of one carbon-carbon sigma bond. So C is the correct answer. So we're looking for, again, species that have to start with basically quaternary carbons, so that when you cleave them, you're going to get a tertiary radical. And you can imagine octane, since it's linear, there's no branching. It doesn't have anything that's tertiary or quaternary to begin with. The 2,5-dimethylhexane, we saw that in the two prior problems. There's no bonds that you could cleave there that would generate anything that's tertiary. The same for 3-methylheptane. So let's just go ahead and draw out the 2,2,3,3 tetramethylbutane, and basically what we're looking at doing is cleaving the central bond homolytically, and then what that is going to generate are these tertiary radicals, so 2 of them. And again, you can only get that from a branched isomer. And so it has to be, fairly branched at that, so that you generate a tertiary radical to begin with. So question 5, the answer is C. The product when 2R3S 2-chloro-3-methylpentane is hydrolyzed in water. So let's just go ahead and draw out the structure. So pentane is 5. 1, 2, 3, 4, 5. We have 2-chloro, 3-methyl. And so the stereochemistry here really it's a distractor in this question, because if you look at the conditions, you're treating with water, and there's no strong nucleophile, so it's going to be an SN1 reaction. The chlorine is ionized, so that goes away. So minus Cl minus. You get a carbocation that's secondary. You're looking at your beta prime. Carbons, you can see that you can get a 1 to H shift from beta prime. So this will migrate over. You now get a tertiary carbocation, and so this is achiral. It will be trapped by water. You'll ultimately get the alcohol after proton transfer. So 1, 2, 3, 4, 5. That's your 3-methyl 3-pentanol shown here. So again, the stereochemistry that you were given to start with in the nomenclature is just a distractor under the SN1 conditions. So moving along to question 6 on chemophysical properties in section 2. We're dealing with the free radical substitution of 2,4-dimethylpentane. So let's just go ahead and draw that out. So 1, 2, 3, 4, 5, 2, and 4. And so if we look at this and we determine the unique sets, we can see that there's 3 unique sets of H. So methyl, 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 that's 1 set. So that's 3, 6, 9, 12. Methynes, that's 2. Methylene, that's 2. So let's go ahead and capture that. We said 12, 2, and 2. Another thing we can do is classify them. So primary, tertiary, secondary, but it says we're using chlorine. Chlorine's going to go ahead and chlorinate any of those, really. And so what we're doing based on this question is using the statistics. So we calculated how many of each there are. So 12 plus 2 is 14 plus 2 is 16. And then you're just taking the ratios from there. So the primary ends up being, so primary is equal to 12 over 16. Then secondary is equal to 2 over 16. And the tertiary is equal to 2 over 16. So this gets you, if you divide by 4, 3/4, then 1/8, then 1/8. And so that gets you the 1/4, that gets you to 1. So primary equals 75%. And then the two secondary and tertiary gives you 12.5 and 12.5. So that was purely based on counting the H's. Then question 7, we're looking at the enthalpy change for this reaction in which we're cleaving a carbon-carbon sigma bond. Then we're cleaving the bond in hydrogen, and then we're forming ethane and methane. So you're basically going back to the table and looking up these values that are shown. So on the reactant side, the values are positive. On the product side, they're negative. And when you do all the arithmetic there, you end up with negative 54 kilojoules per mole. So our next question is, we're taking R, 2-chlorobutane, and subjecting it to monochlorination. So basically, we already have a chlorine in the molecule. Let's go ahead and just draw that out. So there's butane, and when we do the stereochemistry for the R, it's going to be a wedge that's pointed out towards us. So that's R2-chlorobutane, and it's saying now if we're going to chlorinate that with light or heat, how many dichlorinated products would we get? So again, the first thing to do is figure out from the starting material how many unique sets of H, and we can count 1, 2, 3, 4. So there's 4 sets. They're going to be a ratio of 3 to 1 to 2 to 3. And from this, you can either draw out substituting an H for a Cl, or you can, if you can, just visualize it. In the methyl group, if you substitute H for Cl, that's going to generate 1 new dichlorinated. So I'll just put dichloro. If you substitute out the H on the second position, that generates 1 substrate. Now, the third position here, carbon 3, you have 2 hydrogens shown there. But if you substitute them out, you're actually generating a new stereocenter there. So you can generate an R or an S. So you're actually going to get 2. So that will go to 2. Then the final position 4, if you substitute that out, you're only going to get 1. So when we do that math, we have 1 plus 1 is 2, plus 2 is 4, plus 1 is equal to 5. And so let me just draw all those out for you because we're going to need one of them in question 9. So that center is not changing. It's always staying what it is. If you substitute at the first position, now if you substitute at the second position, that stereocenter goes away. Now substituting at carbon 3, that stays the same, but now you can have the chlorine going away from you, or the chlorine going towards you. And so again, this center is set as R, so it's already staying R. And then in the new compounds here, you're basically you're figuring out from the Kahn-Ingold-Prelog what those would be. So let's just go ahead and do the one with the wedge first. So this is going to be R. This is going to be S. So priority 1, priority 2, priority 3, That's going clockwise, so that's R, and then this has to be the opposite, so S. Let's just draw the last one for completeness. And again, that stays as the R. So there's your 5. And then question 9 is asking you about this specific isomer here. The 2R, 3S, will it rotate plane polarized light? And the answer is no, because when you do a bond rotation about that bond, and then you redraw it, you will find that that chlorine is now coming out towards you, and essentially what you have now is a meso compound. So the specific rotation will be 0. So the last question in this section, question 10, the answer is A, but how did we arrive at that? So we saw from the prior question, the prompt was using R2-chlorobutane, and the student wants to use sodium azide, so a strong nucleophile, to convert it into the S2-azidobutane. So because the inversion has happened, an SN2 reaction is required. So the prompt says there's a solvent bottle in the lab, but the label was worn off. The student ran the experiment anyway. They analyzed it in process using thin layer chromatography. The chloride was fully consumed and a new product was formed. And after the product was isolated, it was measured in a polarimeter and found to be 0. So what is the solvent? And so if you're looking at, SN2, so there's the structure of acetone, the structure of DMF, the structure of DMSO. So these 3 are all polar aprotic, so they're good SN2 solvents. And so if one of those was used, the specific rotation would not equal 0. But because the specific rotation does equal 0, that means ethanol was used. And we know that because this is a polar protic solvent, and therefore under these conditions the mechanism would have been SN1. So again, the ethanol would have helped ionize to the carbocation, which is achiral, that would have been trapped, giving you a racemic mixture of product, therefore no specific rotation. So section 3 is predict the product. So you're given the starting material, some conditions, and your choices. And so really what you want to do here, the first couple things, is you're looking at the starting material. What are the main functional groups? Okay, we're starting with a secondary alcohol. We're treating with a polar protic solvent, so we can say the mechanism's probably going to go by SN1. And again, that's going to proceed through a carbocation, and we already characterized the alcohol as secondary. So it's going to form a secondary carbocation. I'll draw that structure here. So that's what happens after ionization. And so we have a secondary carbocation, and you're looking at the beta carbons, so beta prime. We can see that beta prime is not going to do us any good because we cannot have degenerate rearrangements. But beta we can, or beta prime we can. We have a 3-membered ring, so that has strain. That's going to want to expand And then when it does, it's going to form a 4-membered ring. So I'll draw that up here. And so it's going to go from 3 to 4. Now you have a tertiary carbocation that can get trapped. So 5, 4, where you're starting with 5, 3. And so our answer is going to be C. So again, we can eliminate A because we know that we want to relieve this strain here. Again, B would be if there was a hydride shift, but that would be secondary to secondary, so that's not allowed. And then D, the ring sizes are incorrect, so it can't form 5. 12, we're starting with a secondary alcohol, HBr, so polar, protic, so it's an acid. The alcohol gets protonated, it ionizes to a secondary carbocation. You're looking at beta, beta prime. So beta is tertiary, beta prime is secondary. So we're going to go towards beta in terms of a hydride shift. So that means the trapping by the Br minus should be at that position, and that's going to be B. C is sort of nonsensical because you have now a substitution at the methyl group. D is retention, and we know that if a carbocation can rearrange, it will. And then A is going in the wrong direction, as we said when we evaluated the beta carbons. 13, we have a situation here now with 2 functional groups. So a secondary chloride, a secondary iodide. Iodide's the better leaving group. We have a good nucleophile bromine. We have a polar aprotic solvent, so this is SN2. So there's going to be an inversion, which means the bromide anion attacks opposite the iodine. So the bromine needs to be now equatorial, and that hydrogen that was equatorial becomes axial. So our correct answer here is D. So I'll put that hydrogen in so you see it. Nothing's going to happen at the chlorine, so that stays the same. And again, the bromine ends up equatorial. Question 14, we're treating methyl triflate. Again, it's important you know what the abbreviation of triflate means. So that's a good leaving group. And so you're going to substitute that off for this strong nucleophile. And again, if you draw that out, you'll find that it's an alkyne anion. And so this question is asking you about nomenclature. So you have 3 carbons, then you're adding 2. So you're ultimately going to get 5 total carbons. And the start of the triple bond is at carbon 2. So our answer is D. You can eliminate that because it's not an alkyne. You can eliminate that based on carbon count, and you can eliminate that based on the start position of the alkyne. Question 15. We have an alcohol. So primary alcohol, primary bromide. We're treating with a base and a polar aprotic solvent. So the base is going to abstract this H here. You're going to generate an alkoxide, so O minus Na plus. And so now you have a good nucleophile in the presence of a leaving group, But again, it's all in one molecule, so you're going to form a ring. So what you want to do is number the atoms that are going to be in that ring, starting from the nucleophile 1, 2, 3, 4, 5, 6. So you're forming a 6-membered ring. Now again, what's important is you realize where the substituents occur on that ring. So if we look at question or answer A, and we start numbering 1, 2, 3, 4, 5, 6. Notice that the methyl groups have to be on position 3. Here they're on position 4, so we eliminate A. Let's do the same sort of thing with the blue pen for B. So 1, 2, 3, 4, 5, 6. So that looks like it's going to be correct. C, we have 1, 2, 3, 4, 5. That's not a big enough ring. It's a 5-membered ring. So 6, 6, 5. We can eliminate D because it's 5. So B is the correct answer there. So when you're doing these sort of analyses, a helpful thing to do is number the carbons or the atoms as you go along. Again, it doesn't necessarily have to be the IUPAC numbering for the name itself, but just something you can track the substituents with. Our next run of questions in section 4 are pick the reagent. So you have starting material is given to you. The product is given to you, and you're asked to choose between A, B, C, and D. Which conditions affect that transformation? So again, as normal, what you want to do is identify the major functional groups, in this case an alkene. Now you have a secondary bromide with retention of the alkene, and so this is actually an allylic position. So just by writing that down, you start thinking, okay, it's an allylic bromide. Look at the conditions, F2, F's not in the molecule. Sodium bromide, this is an SN2 reaction. Now you have C and D. Those are starting to look more like things that could affect that transformation. And so overall, what you're doing for 16 is a CH to C bromine, so it's a radical mechanism. The alkene is retained, so it cannot be D, so therefore C is the correct answer with NBS. So this is N-bromosuccinimide, and that will carry out the allylic bromination. 17 is B, and so what are we doing here? We have a benzene ring, a cyclohexane looking thing. Not quite, because it's attached to the benzene, but overall we're doing an H to Cl substitution, so it has to be radical. So conditions A, this is an electrophile for SN2, so we can eliminate that. B is the correct answer, chlorine and light. C is SN2, you have this strong nucleophile polar aprotic solvent. D is incorrect, you have an acid and water, so this is more of SN1. So again, C is you're doing the H to halogen, so it has to be radical. 18, you have a secondary bromide. And we look at the product, there's been an inversion. So we're thinking SN2 mechanism, so we need a good nucleophile that has nitrogen in the rest of that molecule. We start looking from A to B to C to D. That does not have everything that's included in the product, neither does sodium azide. C could possibly be it, but look at the difference between C and D. You have NH versus N minus K plus, so this is a good nucleophile. it's got DMF, a polar aprotic solvent. So D is going to be the best response for this. Again, just because of the ionic nature of the sodium or the potassium thialimide. So moving on to 19, we have secondary chloride. It's allylic. It's allylic. We also have this oxygen here that's enriching the double bonds. And then if we look at the product, we've done basically a substitution at that position. Notice there's no stereochemistry shown. So that's another clue. And basically we have to figure out the name of this thing. There's 1, 2, 3. So 3 carbons, and then we have an alcohol at the 2 position and a methyl group at the 2 position. So that's some more clues. 2-methyl, 2-propanol. Is that alcohol? Again, draw stuff out. That's 1-butanol, that doesn't match. Ethanol doesn't match. 2-butanol, that doesn't match what you see is being substituted. So 20 is C. We have an alkene. And we notice in the product it's no longer there. We have a secondary bromide. So we need to do a radical addition to the alkene. So this is sodium bromide, that's SN2. Bromine and light, we don't want to use that because that's not going to give us the desired product. There obviously D has no chlorine in it, so the HBr peroxide, again, that mechanism will generate basically the bromine radical after the oxygen radical is formed. So that is what is the reactive species here, is that bromine radical then adds to the alkene. And so a slightly new format for this exam, section 5, mechanisms. So we're given a reaction and then we're given the choices about the different steps present. So again, what do we want to recognize here? We have a secondary chloride. We're treating with a polar protic solvent, formic acid. And then what we recognize where that that chlorine initially was, now there's 2 H's. And then over where the methyl group had an H, that's been now substituted for the solvent / nucleophile. And so if we're thinking about mechanisms, you know, if an SN2 happened, it would have to happen at that carbon bearing the chlorine, but the substitution has happened somewhere else. So we're thinking SN1. And so that will invoke a carbocation and potential rearrangement. And so between the choices for A, B, C, and D, you're given the different mechanistic steps. And then the questions are asking you about what they are. So ionization, so that's the loss of the chlorine. So that's B. That's forming a secondary carbocation. So the rearrangement is A. Again, you're looking at beta and beta prime. So beta is secondary, beta prime is tertiary. So you need to go to secondary to tertiary, that's allowed. Secondary to secondary is not allowed. The trapping of the carbocation, that's D. So you've now done the rearrangement to form the tertiary carbocation. It's trapped by the solvent. And then the proton transfer is movement, is abstraction of that H, either by the water or by the formate in the solution. And then finally, what's the C13 1H ratio, the uniqueness. And so let's just do the carbon count. So we have 1, 2, 3, 4, and 5. So we can eliminate B right away. Then hydrogens, we have 1, 2, 3, 4. So we need 5 and 4. So that basically eliminates A, eliminates C, and gives you D as the correct answer. And so you have 4, 4, 3, and 1 as we're going in descending order. And so now we're moving on to the spectral elucidation using the IR, mass spec, and NMR data. So really, what you can pull out from the IR, you're looking at region 3 here, and so you're between 17 and 1800, so about 1750. That's telling you there's a carbonyl, so you know that there's going to be 2 things bonded to it, but for right now you have a C and an O and 1 degree of unsaturation. So CO, 1 degree of unsaturation. You'll also notice in region 1 there's the lack of anything here. So if we were taking notes, no OH, no NH. So you can think about that. There's no alcohol, no acid, no amine, based on the classification. So primary, secondary, no amide, again primary, secondary. So your structure should have none of that proposed in there. And so on a couple of the videos people made, they're commenting on this, and really all this right here is telling you is CSP3H. That's all that's telling you. But all molecules will typically have that. So you really can't make any inferences other than, okay, it's your normal CH stuff. You can look over here. There is no signal here. So if you make another note, you can say no aldehyde. So based on all of that, what are you left with in terms of the carbonyl containing functional groups? So you're basically down to ketone or ester. So really this has 1 oxygen, 2 oxygens. And so if we ignore stuff below the fingerprint region, this may or may not be a C sigma bond O found in the ester. So we don't really know that for certain. What we do know is there is carbonyl. Now, it's either ketone or ester, but we haven't figured out, is there a second oxygen yet? We can't make that claim for 100% confidence just yet. Okay, so a bit of a snafu here. I forgot to hit record. I wrote a bunch of stuff down on this slide already, but what I'll do is I'll go back over it with the laser pointer here to highlight what I was saying. So in the mass spectrum, the x-axis is mass to charge, m to z. So mass divided by charge, where z is typically 1. So what we're dealing with is the mass. I know it's it's hard to see, but in the spectrum here, there are 2 little blips down here. And what I did is I copied the numbers into this table, so M to Z, and then the intensity of those signals. Again, you can't see them here because they're 1%, they're sort of in the baseline, but the mass here is increasing. So you see this 88 here, that's the tallest peak. At 100%, that's called the base peak. The peak with the highest mass, 194, that's called the parent. The parent contains all of the elements in the molecular formula. So I've written that there. 194 contains all the elements. At the m plus 2 of the parent is 196. So the difference between there is 2. Now the 1-to-1 ratio is observed in the intensity, 1 to 0.9. So that's the 1-to-1 ratio. There were some mistakes in the videos where people were saying 88 and 89 is present in a 1-to-1 ratio, and that's not true. Again, the base peak is whatever peak is 100% intensity. That happens to be 88. At 89, you see this signal at 4.9% intensity. That results from the C13 contribution that naturally occurs with carbon. But for these other clusters, 121, 123, that's 1-to-1. And you have another cluster that's 1-to-1, and then a third cluster that's 1-to-1. That's indicative of bromine. So that's how you know that the bromine is there. So let's go ahead and write that. So all elements, then we said bromine. So we're going to subtract out 79. So when we do that, we get 115. And again, now that's containing carbon, H, and we know from the IR at least one oxygen. So let's go ahead and subtract out, at this point, one oxygen. So we do that, we're going to get 99. So now again, the thing we're dealing with here is there another oxygen because it's an ester, or is it just one for being a ketone? And so I'm just going to answer the question here because this software, I can't skip back and forth. I have to proceed through the PDF sequentially. But when you go to the carbon NMR, you'll find that there are 6 unique signals. And so we're going to use that number, the 6, and then stick it back into this 99, and then we're going to finagle out the hydrogen count versus the oxygen count. And you'll recall we did this way back in module 2 when we were dealing with testosterone. And so again, I would now fast forward and show you the carbon count, but based on the way this software works, I can't do that. So we had 6 times 12, that gets us 72. C count from carbon 13. And so we subtract that from 99 and we get 27. And so when we're talking about 6 carbons, you know, what is 6 carbons in an alkane? CnH2n plus 2. So C6H2 times 6 plus 2, C6H12H14. So with 6 carbon atoms, the maximum number of hydrogens is 14. So if you just put that in there now, so 14, and you subtract that out, you're going to end up with 13, and that's like a weird number, right? Because we know from up here that oxygen's 16, but we can do some more accounting for things that we already know. And so what do I mean by that? We're using, this as the maximum number of hydrogens, but we already know it's not the maximum number because we have a degree of unsaturation from the carbonyl group. So 1 degree of unsaturation. So what is that doing? It's taking this down to 12. And so what does it ultimately do over here? It bumps that number up by 2, right? So plus 2, that equals 15. That's still not quite right because we know oxygen is 16, but when we're doing this, we already said that there's a bromine present, and bromine is equal to an H. So we need to subtract out from this 12, C6H11, and so add that difference back into here. That gets you the 16. And so that's equal to another oxygen. So you're at C6H11 BrO2 for the molecular formula. And again, I know there was, some people making claims by looking at the IR that it's automatically an ester, but you can't really 100% do that without refuting, the ketone molecular formula. So again, based on the nature of the software, I would normally flip back and forth and explain this, but I have to do it sequentially through these slides. So let's go ahead and move now onto the next piece of data. So we're at the proton NMR now, but we already, determined from the prior slide, we had C6H11 BrO2. So how do we actually come up with the 11 from the 1H NMR data? So in some of the videos, what I saw a common theme was, looking at the multiplicity and then talking about the neighbors, and that's perfectly fine. But again, one thing you want to do is establish the ratio first, and then talk about how the neighbors will confirm your final claim. So let's do this first. Find the unique sets. There's 1, 2, 3, 4, 5. So 5 unique sets. And these numbers here are telling you what the ratio is. So, it says 1, 1, 1, 1, 1, and then this says 1.5. So really you have to multiply them all by 2. So you end up getting 2, 2, 2, 2, and 3. And so that's your ratio, 3 to 2 to 2 to 2 to 2. And so what now is that telling you? Just convert it to what you know. What are 3 hydrogens? That's this fragment. It's a methyl group. 2 methylene, and so you have that a total of 4 times. And so those are those fragments. And don't forget, your other fragments. You had a bromine. So this bromine is obviously going to be bonded to a CH2 at some point. So maybe we can just go ahead and do that. So we'll take one of these out. We'll do it this way. CH2, Br. So that takes care of that. That takes care of that. Well, we know that this CH2, it's going to be bonded to something else. It can't be bonded to CH3 because then you're making a compound and that's done. You can't do anything else with it. We know we've accounted for 5 carbons here. We know from the IR there's a carbonyl. That's the 6th carbon. We could bond it to that, but that wouldn't make sense with the multiplicities. So let's examine those now. We have 4 lines, it's a quartet. 3 lines is a triplet. 3 lines is a triplet. 1, 2, 3, 4, 5. That's a pentet or quintet. 3 lines is a triplet. So now we can put under there. So a quartet comes from 3 neighbors. A triplet comes from 2. 2 and 2. A pentet, so 5 is equal to 4 plus 1. That is 4 neighbors. So if you have your methyl group that integrates to 3, so that's this signal right here. So integrates to 3. It has 2 neighbors. So you can use one of these CH2 groups and bond it to that methyl group. So we'll take care of these. Now we have these fragments, CH2, CH3. And so we can do some further analysis here and look at, see this gap here? So this gap is basically telling you at some point these 2 signals to the left of that gap are bonded to heteroatoms. And so when you look at the fragments that you've drawn already, you have a CH2 group that's a quartet. CH2, that's a quartet because it's bonded to the methyl. Now this has to be bonded to a heteroatom. But this CH2 is already bonded to a heteroatom. So this CH2 has to be that CH2, and that CH2 has to be bonded to a heteroatom. The only heteroatom left is an oxygen. And so this can now become fragment OCH. CH2, CH3. And now we know from that there's the sp2 hybridized carbonyl from the IR. So we should go ahead and just bond that stuff together. So use some shorthand there. And so we've now taken 3 carbons and then 5 of the hydrogens. And so you're left with, this triplet. It's going to correspond to that CH2 group because that is a triplet. That means it's bonded to another CH2 group. So we can modify this now. So we take out one of these, we make it CH2, CH2Br. And again, you can make these assignments of this being bonded to the carbon bearing the bromine and this being bonded to the carbon bearing the oxygen based on the tables that were given you in the back. Again, the oxygen is going to push it further downfield than the bromine. And then finally, what do you have to do? You have one more CH2 group. So you have to bond it to this fragment. So CH2, CH2, CH2Br. So this gives you your triplet. This is blocked, so that's a triplet, and then this is the pentent. And now you have your two main fragments here, this and this, that you need to connect. And so that's the claim thus far using the proton data. So it's an ester. So now we're going to move on to the carbon data. And one thing I want to point out about the data that's shown, so even though I didn't explicitly mention it on this exam, it has been mentioned in lecture. This cluster of peaks here is not in the product. That's the solvent in which the sample is dissolved. So you're not counting those signals. A lot of people did count that in their videos. If you go to the top here, this is telling you the chemical shift of that signal. So you can count that 1, 2, 3, 4, 5, 6. So that's where you get your 6 unique signals. And again, I would have hopped forward to this in the mass spec slide, but I can't do that. 6 unique carbons. And we already know that that is the carbon of the carbonyl, which is sp2. And then you have this cluster here. These are all sp3. So there's 4 of them. And so again, you would flip back and forth between this and the DEPT, which we'll do now. So this is on the bottom, the carbon you just looked at. So this is solvent, we don't consider it. In the DEPT NMR, which is this one that is stacked above it, you can see that this signal shows nothing here, so that means there's no attached H's. Then the key is telling you that if the signal is negatively phased or going down, it's a CH2. And so you count 1, 2, 3, 4. So there's 4 CH2 groups. Then you have this group going up. It can be CH3 or CH, and we already know that it's CH3 based on the proton NMR data. So this is what the structure ends up being, and this is called ethyl. That's the ethyl group. There's 4 carbons there. Because this is an ester, it's called a butanoate. There's a bromine at the 4 position. So 4 bromo butane and then OATE. So ethyl 4-bromobutanoate is the structure of this compound. So one person got it exactly right on the exam. Another person got the isomer when the oxygen was over here. And in the videos for the redo, There were some very good ones that explained things very well, very succinctly, and those got full credit. But we'll go ahead and answer the last couple questions here that should have facilitated your thought process on the elucidation. So, as we said before, we can eliminate the acid, the amide, and the aldehyde based on the IR signatures. That leaves us with the ester. Again, this is a clue that there's 2 oxygens. There's no chlorine, there's no nitrogen. So there's a bromine plus the 2 oxygens. There's 6 carbons by the C13. There was 5 unique sets in that ratio by the 1H. And then using all that information, we put it together to get the ethyl form bromo butanoate as the final structure.